So my name is Chris Baines. I'm an engineer at Google, and I work on the support library, which is exactly what I'm going to be talking about. So when I first started writing this talk about 5 days ago, I was trying to think of something interesting to say. My original sort of submission for this conference was wishy-washy. I can't remember what it was, like design the design library or something. But that topic's been gone over loads and loads and loads over the past couple of years. So I was trying to think, what is interesting? What do you actually want to hear? So I had to think, and I thought, well, what's in my head? Over the past couple of years, we've been writing the support library, and that spans, well, what was API 4 up to whatever's current 24. And across all those different API levels, there are so many things we've had to do to actually make stuff work. So many workarounds, interesting features, bugs we've had to work around, device issues, whatever it is. So I thought, I'll talk about that. Now, I had 6 kind of sections planned. Can't hear? Is that better? Yeah? Okay. Is that better? No. Right, so I had 6 sections planned, all to do with either a bug we've fixed or a feature we've implemented. Now, as it turned out, I've only got 2 because that's all the time I've got. So, before I start, I've put the slides at this URL. That's mainly for the people on live stream if you want to follow along. Baines.me/DC NYC16. So the first feature we're going to talk about is day-night. This was added in app.compat in 24.1, if I remember rightly. And that allows your app to be automatically themed based on the time of day. So here we've got an app which is, well, a device which is at lunchtime, like 12 o'clock in the afternoon, and it's light background, dark text. And then automatically, when the device is opened at 10 p.m., it's dark background, light text, and that's to reduce glare for people. So to actually use that in app.compat, you change your theme to theme.app.compat.day-night, and then you also need to tell app.compat what mode to use. And you use that via one of 2 APIs. The one mentioned here is set default night mode, but there's also a local override version on an activity. That takes one of 4 options. The first one being follow system, and that tells app.compat to just follow whatever the framework is using. Now, there isn't actually a night mode automatically engaged in the framework currently, so that is just pretty much where the default is. Then we have auto, and that will change the theme between dark and light based on the time of day. If your application already has location permissions, like if it's already requesting them, app.compat will get the last known location and then try and work out a sunset and sunrise time based on that location. If you don't, it will use some hard-coded values, those being currently 10 p.m. and 6 a.m. And then the other 2 values are yes and no, which do pretty much what you'd expect. Yes being that always night mode, no being day mode. Try not to use these APIs too much. They are mainly for when you have sort of preference or a setting in an app. Otherwise, you can just change the actual base theme of your application to the light or the dark variant, and it's much more efficient. Now, night mode has actually existed in the framework, in the sort of Android, since API 8. And it was exposed via 2 resource qualifiers, -night and -not night. But the trouble is, they were only actually used when 2 situations occurred. Number 1, you were in car mode, and number 2, you were docked. So you can see a Motorola Droid, I think that is, running the Claire. And night mode is only used when it was in that dock, basically. And it was mainly for things like navigation apps. You know, you don't want this bright white background on your device when you're trying to drive along at midnight or whatever. So as with most resource qualifiers, they are sort of controlled via the configuration class in your resources. Night mode is controlled via its UI mode field. There are so as we all resource qualifiers, well, most resource qualifiers are actually controlled via this class. There's actually one that isn't. I just thought I'd give you a little bit of a quiz. Can anyone guess which resource qualifier, which I guarantee you're all using, isn't controlled by this class? Okay, I'll wait. No one's going to answer. It's SDK level. So that is the only one which is hard-coded in Asset Manager. Everything else will get its value from your configuration or your display metrics. And the good thing about these 2 things is that you can actually update them dynamically in your app. So you can actually control how resources are loaded dynamically, which is exactly what app.compat does. So UI mode controls a number of different things. Night mode is just one of them. So to actually set or get the value, you have to use this mask value, and that will give you the actual int. Once you've got that, it is set to one of three options. The first one being undefined, and that is the default, which I'm guessing all your phones are running right now. And what that means is that your dash night and your dash not night resources are completely ignored. They're not loaded at all. Then we have no and yes, which again, do is what you'd expect. No means that your not night qualified resources are loaded, and yes means that your dash night resources are loaded. Now, you might be getting deja vu here because the values pretty much map exactly to what AppCompat exposes as its mode, and that's done on purpose. AppCompat is just basically a little framework on top of the framework. Oh, that's a bit right. To just expose the functionality already provided by the framework. They're actually also the same int values, but that's just kind of a small implementation detail. So here is what AppCompat actually uses internally, well, the simplified version anyway, to set the night mode dynamically. So it gets its resources from your activity usually. It gets the current configuration that your device is running, and then it will update the UI mode field based on whatever the new night mode is. And that will be one of our UI mode night yes or no, depending on what you're actually using. And then it will call resources.update configuration. And from that point onwards, any resources which are loaded, grabbed or retrieved from that resource instance will be using the either dash night or dash not night, depends on what option you're using. Which means that anything inflated after that fact. So it won't automatically update anything that's already on screen. It's only things which are inflated after this call. Which means that things like in your values dash night or draw dash night or raw dash night, whatever it is, they'll then be used. Which is exactly how AppCompat actually works its theme. So as I said earlier, the first thing you need to do is change your theme to theme.appcompat.daynight. And all AppCompat does, that declaration, is this. So the default version, basically light, points to the theme.appcompat.light theme. And then when you're in dash night, it points to the dark theme. So hopefully you've sort of picked up there, not just about day night, but also stuff about configuration, how you actually update stuff. Now, the next thing I'm going to talk about, which is the bulk of this presentation actually, is about app bar layout and flinging. So if you remember, when was it? We released the design library version 22, I believe, so that was a couple of IOs ago. And pretty much straight away, there was a bug raised about flinging. So let's look at it. So here we've got Cheese Square, which is a sample I wrote around the same time. And as the user swipes up, the app bar layout is collapsed. And the user keeps scrolling on a little bit as well. Then the user scrolls down and tries to fling the list. Now, what you'd expect to happen there is that the app bar layout would kind of carry on, like pull down, but it doesn't. What happens is the user needs to swipe down again to actually expand it. So instead of having one continuous scroll, you have got this two gesture thing. So the problem here, quite obvious problem, is that sort of the flinging doesn't actually transfer. So like when the user actually flings and the scroll view hits its edge, the actual velocity, which is sort of remaining, isn't transferred. What we actually want is kind of like this. So the user flings, well, the user scrolls up, then flings down, and it keeps scrolling down. So that's what we want. Before we actually start looking at this kind of stuff and what the actual bug is, it's important to actually take a step back and understand how scrolling actually works in sort of the more basic views, like scroll view or, well, yeah, scroll view. So what we're going to talk about here is on-touch event. So this is just touch handling. If you've ever written custom views, I guarantee you've touched this method. There's also on-intercept touch event, which is important for scrolling views, but we're not going to talk about that here. But if you ever write your own scrolling view, which I wouldn't recommend, you definitely need to look at this method. Right, so let's go through a gesture of a user pressing down the screen, scrolling, and then lifting their finger up. So the first event you'll get is an action down. User touches down the screen. And at that point, this is the kind of implementation which is in scroll view. So the first thing it'll do, it'll get passed a motion event as a parameter. And then you need to create a velocity tracker. You'll see more about why we do this later, but it allows us to just track the velocity that a user is scrolling. And then because we're a vertically scrolling list, and we'll get the Y value that a user has touched down, and then we'll just keep a record of it. that's all we're doing, tap down. And then the user starts moving their finger. Now that is typically made up of like hundreds, maybe thousands of events, depending on how slow they go. But they're all action move events. We handle them all the same, and the code typically looks like this. So we need to add that event to the motion tracker because it needs to be updated at all times. Then we'll grab the new y value. In this case, it's 1010. The previous was 1020. So we calculate the difference, dy, and we work out it's minus 10. Once we've got that, we've got to update ourselves to actually look like we've moved. So this is an implementation. It's not from scroll view. It's kind of what list view would use. So it just iterates through its children and then offsets them all. So it looks like it's moving up. We just use the dy value from the view, so it looks like whatever the user has scrolled is directly moving the views. And then finally, we'll just update the last motion y. So we actually, for the next event, we still know what the last motion y was. And then the user will lift their finger up. At that point, we get an action up event. And at this point, we need to work out whether we need to keep flinging. So if the user will scroll quickly, you don't want it to hit a dead stop. You probably want to keep it to like fling and settle. So that is where this velocity tracker comes into play. So it's a bit of a weird API. The first thing you need to do is you need to call compute current velocity, and you give it an int. Well, it's a long, actually. And that tells it how long to calculate the velocity over. Typically, we use 1,000, because that's 1,000 milliseconds. And then you get the y value, get the y velocity. And that will tell you how many pixels per second the initial fling should start at. You get that, and then you'll check whether that velocity is enough to actually fling. View configuration will give you a min and a max to actually use. I've left it out here because it gets a bit deep. But once you know that you're in a position to actually start flinging, you'll call your fling method. Scroll view actually exposes this as a public method. Most views don't know. So here is roughly what happens in fling. The first thing you'll see is this overscroller object. Overscroller object is provided by the framework for you. It basically handles deceleration of scrolling. So you'll call the fling method, which we'll do in a minute, and it will tell you at all times where you should be in a fling, the x and y value, and when it should stop. So it handles all that for you. You don't need to think about it. So we have this fling method. You pass in the velocity, and then we need to calculate how much we can actually scroll. Each implementation is different. This is kind of what scroll view uses. It's just a scroll range. It's basically the amount of excess that a user can actually move your view. I've left the implementation out, but you can imagine what the value would be. Then you call fling on the scroller. If you ever call this method, I would really advise you to lay out your code like this. The reason why is because the sort of parameter ordering is slightly weird. So the first two values are your current scroll positions. So you pass in x then y. Then you have fling velocities. Again, x then y. Because we don't scroll horizontally, we just pass 0. And then we have the third set of parameters. And they are min x and max x. Again, we don't scroll horizontally, so 0, 0. Then we have min y, max y. Again, we can't scroll past 0. And max y is just what the max we can scroll, so in this case, it's scroll range. And then the final two values are your overscroll values. I won't talk too much about this. The thing to know about this is when you actually scroll and you get a fling, you'll see now that you get like an edge glow, like the blue glow, whatever it is. This value you pass here pretty much directly controls how big that glow is when the fling finishes. And then we need to post invalidate an animation, and that just causes the fling to start drawing. Then, and every draw call in view, this method will be called. This has been there since API 1. It's called compute scroll. It is called in dispatch draw before any drawing happens. And it's primarily for things like scroll view or list view, so it can update its views before any drawing happens, just before. So in here, we call the scroller's compute scroll offset method. And that will return true or false of whether we actually need to move ourselves. If it returns false, we just back out and just leave it. If it returns true, we get what it thinks the current x and y value should be. And then we just move ourselves. So that is the basics of how most scrolling view work. Recycle view, list view, scroll view, whatever they are, they all tend to work the same sort of way. The differences tend to be on how they actually do stuff like recycling or things like that. So now let's move more towards what app bar layout actually uses, and that is nested scrolling. Now that was added in API 21, and the reason why was because actually scrolling nested views together was difficult. So if we look at this example here you've got an outer scroll view, and in it you've got a linear layout, and then deep down in there you've got a list view. Now that was never something we really supported before API 21. If you actually try and do it, the thing that scrolls depends on where the user actually touches, and it just gets a bit weird. So API 21 come along, and at the same time was material. So you've probably seen this video 1,000 times, but it's the user scrolling, app bar layout, well, what would be an app bar layout collapses and then comes back down again. So if you think logically about how you'd actually lay that kind of view out, it'd probably be something like this. So you'd have a scroll view, and then you might have a linear layout in there. At the top, you'd have an image view, and then at the bottom, it'll be a list view, because that content information could be like infinite amount of data. So nested scrolling was created to actually sort of help this and solve it. So I've just mentioned the word, but what actually is it? Well, it's an event system. That's all it is, where scroll events are dispatched from the scrolling view up to its parents. So it's easy to look at like an actual diagram. So here we've got that same video, and it's pumping, as it scrolls, it's pumping events, the list view is pumping events up to its parents, and the parents can choose whether or not to actually observe them or consume them, whatever it is. It's good in that it enables two distinct views which scroll to react to each other, but not be too coupled. So for instance, if you try and use like a recycler view on scroll listener, you are totally coupled to that implementation. Nested scrolling is created so that two views anywhere in the hierarchy don't need to know about each other, but they can still react and still sort of update themselves. So here's the API. I like to think of it in two separate ways. There's the sending side and the receiving side. Sending side being the thing which is scrolling, and then the receiving side being the parent up in the view hierarchy. There's a lot of methods there. I'm not going to go through them all. There's a lot of sort of utility methods, getters, setters, whatever they are. The four important methods to know are these four: pre-scroll, scroll, pre-fling, fling. And then there's the receiving side, which react to those sending. Again, lots of methods. The four you should care about are these four. Just the receiving side are the ones I've just mentioned. So there's two things to really know about the API. The first is the kind of relationship between the sender and receiving side. This is quite obvious, but I thought I'd point it out anyway. So when a scrolling view calls dispatch nested pre-scroll, that will bubble up to its parents, and those parents will have their on-nested pre-scroll method called. And the same thing happens for the four other different methods. The other thing to know about is the difference between pre and non-pre. Pre-events allow a parent to consume any or all of an event, or none even. Anything which the parent doesn't consume is then left to the scrolling view to actually use. And the view then moves itself, it scrolls itself, and then a non-pre-scroll event, just a scroll event, is sent. And that's an observational method. The parent can't do anything at that point, it's just observing. Right, so let's go back to our touch events and see how it actually works. So user touch is down again. Nothing's really changed here. We're doing the same stuff, adding the movement to the velocity tracker, checking the Y values. The thing to know here, which is different, is that we call start nested scroll at the end of it. And it takes one parameter, which is an int, and it controls the axis. So if you're vertically scrolling a list, you'll pass this value, and that tells any parents what is actually about to scroll in what axis. So once that is called, each parent of the stack, or tree, will have their onStart nested scroll method called until one returns true, if any. If it returns true, then it is then the parent which is going to receive all scroll events. So once it returns true and it has it has accepted a nested scroll, the on-nested scroll accepted method will be called. I wouldn't worry too much about this method. It's not really used that much, but yeah, it's there. So then the user starts scrolling and moving. So again, we just get lots of action move events. Things are a little bit different here because this is where the bulk of nested scrolling actually comes into play. So the first thing to see is that we now have this new inter at the top, and that just has a length of 2. And the reason why that we have that is that it's passed straight through into dispatch nested prescroll. And this is to work around the fact that we can't return multiple things from a method. So we're passing this int array to the parent, and the parent writes what it wants to consume into it. That's how we actually get the result back. So once that is called with the dy, so we've calculated what the dy should be, and we're going to let the parent have first refusal on actually consuming some of that event. So that method is called, and then the parent's on-nested prescroll method is called. And from that point, we can actually start consuming stuff. So in this instance, we've got some very wishy-washy kind of methods here. But we've got a variable called amount we consume, and then we're going to do something like prescroll, whatever it is. At bar layout just moves itself, but you could do whatever you want, really. The only thing you need to do is that whatever you actually want to consume out of that dy, so in this it's minus 10, you need to write that into the int array. So here we just want to consume 3 pixels, just as an example. So once we've done that, the scrolling view then gets the value back. And because it's got that dy value, it needs to update it. So it basically just minuses whatever the parent has consumed. Remember, it was minus 3 that the parent consumed, which means that the dy is now 7. So the scrolling view now has 7 pixels to actually move itself and update itself. So once we've done that, we can actually start moving ourselves. So we're not going to show the code again for that. It's pretty much what we did earlier. But we also need to call dispatch nested scroll, that observational method. And that is pretty much what you'd expect. We call dispatch nested scroll with the dy, and then the parent's on nested scroll method is called. Nothing too exciting here. Then the user lifts their finger up. You get an action up event. Again, nothing's really changed here. We get the velocity, we calculate that, and we start flinging. Now, remember when we looked at the nested scroll APIs, there's both scroll APIs and also fling APIs. That's where these come into play. So here's typically what happens. So we'll get that velocity value, and then we'll call dispatch nested prescroll, passing it the velocity value. Once that is called, the on-nested prefling method on the parent is called, and it has 2 options. It can either return true or it can return false. This is where the limitations of nested scrolling kind of come into play, because as soon as a parent returns true, it is responsible for the whole fling. It returns false, then it goes back to the view, and the view does the fling, which is what happens here. In this example, the parent has returned false. That means we actually do the fling ourselves, we start moving, and then we call dispatch nested fling to let the parent observe it. The really important thing to know here is that as soon as this is called, stop nested scroll is called. At that point, nested scrolling is finished. But the fling may still happen. The fling may still be moving, but nested scroll itself is actually finished. So hopefully some of you putting 2 and 2 together and realising what the bug is here. So the problem isn't that flinging doesn't well, it kind of is, but it's not the symptom. So the flinging doesn't transfer left of velocity. The problem is actually more this, that nested flinging doesn't allow us to consume or even observe during a fling. So that is why we've been trying to think of a way to actually fix this. Now the nested scrolling APIs are fixed. We can't really change that or even the behavior. So we're having to add something new. So the thing we're coming up with is something called indirect nested scrolling. Now, this is very much work in progress. The code hasn't even been submitted yet. It's just prototypes on my machine. It works, but it's not finished. Hopefully it will be in a future platform release and support library. So let's look at it. So we've just been talking a lot about nested scrolling. Now, some of you may notice that nested scrolling events are only actually dispatched when the user is touching the screen. That is why we're now going to call them, well, that's what I call them, direct nested scrolling. So that is when they only actually dispatch when the user is touching the screen. But there's a load of other kind of scenarios where we actually probably want to use nested scrolling or something similar, which is why we have this thing called indirect nested scrolling, which we're proposing, which is when the user isn't directly touching the screen. Now, there's a number of scenarios where this is important. The first one we're trying to fix is the whole issue, settling from a fling. We need to know when the fling is happening and how we can actually consume it ourselves. There's also things like being able to set the scroll position programmatically. So if you call set selection on a list view, or I can't remember what the recycle view one is, but whatever it is, if you actually programmatically set it, say from a safe state, nested scrolling doesn't know about it. It's never told. Which comes into play for the next one, which is scrolling from key events. So that's important for things like D-pad, so Android TV, or even things like accessibility services, TalkBack. Some of the ways that it moves that moves the scroll position when you're in accessibility mode is via key events. So at the moment, nested scrolling doesn't work with that whatsoever. So this is one way we could use it. And then there's plenty of others which we haven't actually thought about yet. So let's take a quick look at the API. You're probably getting deja vu here because the API is pretty much exactly the same as nested scrolling. It's just you'll see that there's a new indirect keyword in the method. That's the sending side, this is the receiving side. Again, very, very similar. As we just mentioned, the API is pretty much exactly the same as nested scrolling, but there's two important differences. The first is that there's no fling methods currently, and that is because the whole reason we're creating it is so that we can react to fling, so starting a fling isn't going to really work. The other thing to know is that it works with nested scrolling. It doesn't replace it, it works with it in tandem. So the easiest way to visualize it is via a demo, so this is it. So the user has just scrolled up there, we're not going to talk about that bit. So the user presses down the screen. We get an action down event again. We're going to skip all that DY stuff, we're just going to talk about the nested scroll APIs. So we call start nested scroll because the user is touching down. User starts scrolling. In this instance, we are dispatching nested pre-scroll events and scroll events here. We've already talked about this, there's nothing new. And then the user lifts their finger up. At this point, we call stop nested scroll, just like before, and we want to start flinging. Now at this point, fling will call start nested indirect scroll because an indirect nested scroll has started. The user isn't touching the screen, but we still want to react to something which is moving. The fling then starts happening. In the middle of that, we are calling dispatch nested indirect pre-scroll events and dispatch nested scroll events. Once the fling is finished, we call stop nested indirect scroll. And here's the full demo so you can actually see it all again. So this is actually working. I just need to make it work for all the views. The problem with nested scrolling is that every scrolling view needs to be updated to actually dispatch the events, which makes actually adding stuff to it really hard because every scrolling view is completely different. So recycler view or list view or scroll view, they all actually work very differently. So to make one change which is comparable across all different APIs is kind of hard. But yeah, this works. And I did a great good. I choked, okay.